Everyone, in this lecture we're going to be talking about the circulatory system and its response to exercise. So we'll kind of talk about a lot of the anatomy and the basic structures, and then talk about what's happening as we exercise as well. So the first half is a little bit of a review, and we'll go through it pretty quickly. So remember, when it comes to our circulatory system, it does work with our pulmonary system. So pulmonaries bring oxygen in. The blood goes to the pulmonary circulation to collect that oxygen and get CO2 out, and then it goes back to the heart throughout the body to deliver those. It's also helping to move waste products and nutrients into areas that need it as well. And so one of the big things people do forget about our circulatory system is it does help regulate body temperature, helps pull heat away from areas of high heat and bring them to areas where that heat can be dissipated, like the skin. And vice versa for cold, pulling heat in and bringing it into the inside. And so when it comes to that, we're really looking at that blood flow. The blood flow is crucial to all of these processes. And so there's two major ways we can adjust that blood flow during exercise, and that's to increase cardiac output, so how much blood literally is moving through the heart and through your entire body in a given minute, typically is the way you look at it. Or we can redistribute blood flow. So we can basically restrict blood flow to some areas and have that blood flow increase in other areas. So with the circulatory system, you've got things like your heart that actually pumps the blood. You have your arteries and arterioles that carry blood away from the heart, capillaries where exchange happens, and then veins and venules where blood is carried back to the heart. Basic structures, it is important to know these. Especially the big major structures. I'm not going to spend time going through this. You guys can easily pick through diagrams and should have a basic comprehension of the heart already. But there are two sides of, or two circuits of the heart. You have pulmonary circulation that collects blood from the entire body and delivers it to the heart for oxygenation and getting rid of CO2, and then your systemic circuit, the left side of the heart, which pumps oxygenated blood to the body, collects it from the pulmonary circulation, and collects CO2 to get out of the lungs. And so this is a good representation showing those two circulations, so systemic, pulmonary, and kind of how they work in tandem. So then when we actually look at the heart does have a muscle layer, so that's called myocardium. So that's basically cardiac muscle, and it is a little bit different than skeletal muscle, and we'll look at that, but it has three basic parts: the epicardium, which is the outside heart, the myocardium, which is the muscle layer, and then the endocardium, which is on the inside of the heart. And so it receives its own blood supply. It doesn't actually collect from inside the heart. It has its own blood supply that comes from coronary arteries, so arteries and veins on the outside of the heart. The heart's constantly moving and increasing, and so there's a very high oxygen demand and nutrient demand at the heart at all times, but especially during exercise. And if you've ever heard of someone having a myocardial infarction or an MI, this is simply where a blockage of some sort has occurred in one of the coronary arteries and blocked blood flow to an area of the heart and caused cellular damage. And so exercise can protect from this damage during an MI. If you have a heart that's kind of been used to exercise, it's putting a similar demand, and it helps protect people from MIs. So this kind of lays out those different areas of the heart, those three different layers, and the characteristics and functions. And so always good to know things like that. So this chart does a good job of comparing cardiac muscle to skeletal muscle. And some of the things that are actant and that are present in both are different in both. And so contractile proteins still act in myosin, just like we talked about before. So our skeletal muscles were really long, elongated, and one single muscle fiber was really straight, no branching, where our heart muscle, actually, they're much shorter fibers, and they do branch. So instead of just being one straight line, they can branch into 2 and 3, connecting to other muscle fibers. Where skeletal muscles don't really connect muscle fiber to muscle fiber, heart muscle does. Skeletal muscle, for each muscle fiber, has multiple nuclei, but in heart muscle, because they're shorter and smaller, they actually only have one nucleus. Z discs are still there. They're still striated, so you can see that banding pattern from the Z discs and the M lines and those sarcomeres. It is a little tougher to see in heart muscle, but it can still be seen there. The big thing that changes, though, between skeletal muscle and heart muscle is something called cellular junctions, or intercalated disc. And so skeletal muscles don't have these, but heart muscles do. And these are little kind of openings that connect each heart muscle together to allow an action potential to flow through. So every single muscle fiber in the heart is not innervated by a neuron from the brain. Actually, only a few are. But they receive their signal to contract an action potential from another one. So if one muscle fiber starts contracting in the heart, it will actually signal all the other muscle fibers to contract in the heart as well. And then you can see that there's only one kind of layer of connective tissue instead of the multiple that are there with skeletal muscle, mainly because the forces aren't quite as strong that need to be transferred like they are in skeletal muscle. So it continues. The heart is mostly aerobic energy production. Skeletal muscle can be a combination. Calcium is huge, and there's actually extracellular calcium that's always floating around to be utilized in the heart muscle. The heart also is involuntary. You can't just tell your heart to contract like you can your bicep. And so regeneration isn't really possible in heart muscle, and not necessarily very common in skeletal muscle, but there is some evidence of that as well. So exercising does exercise training protects the heart from, as we talked about, MIs, myocardial infarctions. It helps to also reduce the chance of even having those, but if you do have them, better protection because the body is better able to make energy and deliver more oxygen, and it's just healthier in a lot of ways. And part of that could be through things like antioxidant capacity and more sensitive calcium channels and ATP synthesis in those pathways, because during exercise there may be small portions where the heart could use a little more oxygen, and so it learns how to utilize that. And so if you ever do experience an MI, you're less likely to have major heart damage from it. And so this just shows you the injuries from heart attacks in untrained versus trained is much lower. So when it comes to our heart, we can also define it by cardiac cycle, so kind of the movement. And so there's two phases of the cardiac cycle, and that's systole, where the heart is actively contracting and sending blood through the body. Your heart is literally ejecting blood into the pulmonary and systemic circulation. And there's diastole, which is where the heart is relaxing and it's not actually working. The muscles relax the blood. Blood is coming into the heart to fill it up so that when it does contract again in systole, you can deliver that blood. And so in the ventricles, the bottom half of the heart, every time your heart pumps, you deliver about 2/3 of that blood into the body. So it's not, you don't get rid of every bit of blood in the heart. You only get rid of about 2/3, but that's a good thing. So at rest, when you're looking at this cardiac cycle, the diastolic time is longer than systole. So that contraction period, it's a lot longer at rest. During exercise, what happens is that the systole time actually stays the same, and the rest actually gets shorter and shorter and shorter. So the faster your heart rate goes, the less time your heart's at rest, and the less time your heart has to fill with blood. And so things have to occur so that we make sure we get enough blood into the heart for it to pump out into the body. Systole does get a tiny bit shorter, but really, for the most part, systole stays about the same timing, but diastole gets much, much shorter, and the faster the heart rate is, the shorter it becomes. And so you can kind of see here, there is, like I said, a small change, but it's very minute, but that diastole changes a lot when you start increasing that heart rate. And so these cardiac cycles are important because it also leads into blood pressure. Most people have kind of heard about blood pressure, and basically blood pressure is two numbers. Typically here it is 120/80. So 120 is the systole number. It's where the pressure is the highest in the arteries when the heart's contracting, and the diastolic number, usually the lower one, that's how much is on your arteries at rest. And so it's showing how hard your heart has to work in order to move blood through your body and how much resistance your heart has to overcome to move that blood. And so pressure in the ventricles is low during diastole. It's low in your arteries, lowest in your arteries as well. Your heart is filling full of blood from the veins, but also from the atrium, filling that up. And in systole, the pressure rises in your ventricles until it can overcome enough pressure to move that blood throughout your system. And so you can also look at these valves as well as when they open. And so what happens is when the heart contracts, you close what's called your AV valves, so your tricuspid and bicuspid valves. And then your semilunar valves will open up to send blood throughout the body, and these kind of give the sounds that you hear. If you ever put your ear to someone's chest and you hear this kind of lub-dub sound, dum dum, lub-dub, those are actually the sounds of the valves closing in your heart. The first sound you would hear, that first lub sound, is a closing of the atrial ventricle valve, so closing of the ventricles as the heart starts to contract. And the second one is the closing of the aortic valves when they snap back shut when the heart's no longer pushing blood throughout your body. And so you can see these graphs are really, you've probably seen these before, but these graphs are really good to show you how the pressure in the ventricles goes up. And you can see this opening, the closing of the valves with this first sound and this blue. And then blood starts leaving the heart, and it starts coming down as it empties. And then the second sound right here is the closing of the semilunar valves, and that happens when that pressure falls below your diastolic blood pressure because it can no longer force blood out of the heart into the arteries. So we kind of touched about this a little bit, jump ahead sometimes. And so there is something called pulse pressure, which is good to know, which is the difference between systole and diastole. So if you had 120/80, pulse pressure is 40. You simply subtract the two, and that just shows you how much force is needing, or what the difference is between systole and diastole. So how much more the heart is giving than it has to move that blood. Another thing that can be helpful is when looking at exercise and trying to gauge on what these measurements are used for is how much of a load is being put on the heart during exercise or during rest, and is something being dangerous for someone where it may cause a heart attack. Is mean arterial pressure, and this is the average pressure on the arteries over that heartbeat, and you can even do it over time. So the equation is there, and it just gives you an overall kind of look at what's happening at rest. Realize this percentage here changes a little bit because it's but this equation, you basically find that you're finding your pulse pressure, and then you're multiplying it by a third and adding it to diastolic pressure, and it's really about what's the average over time. This third would kind of change a little bit if you're exercising because you're in systole longer than you are diastole, and so that changes a little bit. So mean arterial pressure is mostly used at rest. There are some adjustments you can make to use it during exercise, but it's not commonly done. But it's kind of an overall pressure and can help diagnose certain issues with the heart. So hypertension exists, and so this is considered high blood pressure. Hypertension is defined as either having a blood pressure over or equal to 140/90. Realize that either number puts you at hypertension. So if you had a blood pressure of 140/80, you technically still have hypertension, or if you had a number of 120/90, that would still be considered a high blood pressure. So when it comes to it, there's a lot of people that will be diagnosed with hypertension throughout their lives. Once you're diagnosed with it, pretty much you keep it. Once you're diagnosed, it's not really something you get rid of, but it can be managed several ways. When it comes to primary hypertension, the cause is really unknown. There's a lot of factors that play into it, and this is most hypertensive cases. Just not exactly sure what causes it. It's just something that occurs. But there is secondary hypertension that is caused by other disease processes. But they're both kind of looked at the same. They both increase your risk for heart attacks and heart damage over time. And so there are risk factors for hypertension. So some of these things that may put you more at risk for it is something called left ventricular hypertrophy. If you've had kidney damage or a stroke, or if you've had a heart attack or something like atherosclerosis. And so hypertension can be treated with medication, but we also know that hypertension can be treated with exercise, regardless of the reasoning why. For the most part, there are some exclusions in everything that we talk about in medicine. And so these are kind of, some of the things we look at, but the biggest thing is looking at how you measure and what you're actually measuring with blood pressure and how that's measurement. You guys can take a look at this, read about it in your book. It's something you'll go over a little bit more if you ever get into a realm where you test with it, or if you take a class in this or need to use it. But it quickly lays out what you're kind of looking at. It does well. You can even find some videos that demonstrate this, but not something I'm overly focused on at the moment. But we do kind of look at factors that influence this mean arterial pressure and blood pressure, and really what that's going to translate in is to overall blood movement. And so you have things like cardiac output, how much blood is being moved through the heart at a given time, or vascular resistance, so how hard is it for blood to move through your vessels, can give you this mean arterial pressure. And so there are things your body's always trying to do to adjust this in the short term to make sure it stays in a good level, especially if you're doing something like exercise. So the sympathetic nervous system can change how large our vessels are. And if your vessel is larger, it's easier to move blood through them because, think about like trying to drink water from a straw versus trying to drink water from a garden hose. You're going to get a lot more water out of that garden hose. And so that's that vascular resistance. And so that can change with our brains. And there are receptors that pick up this pressure and can increase and decrease kind of this vascular resistance. Long term, though, if you're in a state where you constantly have high blood pressure or need an adjustment of it, it can be low as well. We tend to do this with the kidneys by just increasing how much water you're holding or decreasing that. And that'll happen during exercise as well. Over time, if you exercise for a long period of time, your kidneys will adjust your blood volume for blood pressure reasons and trying to keep you cool and just maintain blood volume. And so you can see when it comes to blood pressure increases, a lot of different things that can influence it. And so it's not just a simple explanation when these things occur. It's multifactored, and we can look at that. But exercise can definitely help with it across the board. So another thing we want to talk about with the heart is electrical activity of the heart, so how that heart fires. So this is definitely something you should be a little bit more familiar with. We'll go through it pretty quickly, talk about a little bit of it. But basically, your heart is self-pacing, so your heart will contract on its own. It doesn't have to be told to. And this is done through what's called SA and AV nodes, atrioventricular nodes, and sinoatrial nodes. The SA node is the pacemaker of the heart. It fires on its own and really regulates the heart. There are nerves attached to the SA and the AV nodes, and so if the heart needs to slow down or speed up, our brain can tell it to. But if you were to cut those nerves away, your heart would still function on its own. It would actually beat at about 100 beats per minute if there's no brain activity in that. The SA node fires first. That tells the atria to contract at the top to force blood into the ventricles. Then that signal reaches the AV node, which sends the signal into the ventricles, which then cause the ventricles to contract and push blood into the body. There is a brief delay between these just to make sure the ventricles are nice and full, and that's the order it's supposed to happen. Sometimes that can get off, but those are there, and again will happen on its own, but we can speed up and slow this down based on brain activity to cause the SA node to fire faster or to fire slower, depending on what we need. And so this electrical signal in the ventricles is carried through bundle branches and Purkinje fibers to different areas of the heart, and these are very quick. They carry the electrical signal very quickly to then allow the muscles to get that signal and contract in a coordinated effort so that we're pumping blood through the body and not just squeezing the heart's just not squeezing and nothing occurring. So it's a very coordinated effect. And so this is laid out here. Talks about how that action potential is kind of sent and where it's kind of going. And so it is an electrical signal, and so we can look at this electrical signal and tell about health of the heart through what's called an ECG or an electrocardiogram. There are basically it's a graph, and we look at how that graph moves, and there are different components of that graph that tell us different things, and so you can kind of read those on your own. We won't spend too much time here. This is definitely something for another class, but this is an EKG. You see these on shows all the time that looking at the heart, but it defines these P waves and QRS waves and T waves, and showing you what's happening with ventricle contractions and atrial contractions and what's going on there. And so you'll learn more about these. Feel free to read more about them if you're interested, but you'll learn more about these as you do other courses. And these can be used to tell if someone's having a heart attack, if they've had a heart attack, where it's happened, and what areas of the heart might be dead. And so it's a really cool thing. It can also tell things about atherosclerosis and like I said, MIs already. And again, it kind of shows you what that looks like if someone's having an ischemic attack, an actual heart attack, how that normal versus how you have this depressed ST segment, how it goes down much further. But what's happening here is, I think this is a good kind of summary of it all, is it shows what's occurring at each of those stages with the EKG, but also what's going on in the heart of when the wave is depolarizing, so causing those muscles to contract, versus repolarizing in the green, and how that electrical current's being carried, right? And so you follow it down, you can see how it's top down to force blood into the ventricles. They repolarize as the ventricles are starting to contract kind of from a bottom up. They send all of the blood out. That starts to repolarize from the bottom to the top as well, and you complete that contraction, rest for a little while in diastole, and then start the process over. And so this is a good chart, just kind of overlaps that pressure change in the ventricle versus the lub-dub sound, which you've already looked at, and put that EKG wave over the top, so you can kind of, again, follow that process. You should be able to walk yourself through those. And so that goes back to, I keep throwing out this term called cardiac output, and so I've alluded to what that means, but there is kind of some pieces to it. And so cardiac output is the amount of blood that is pumped by the heart each and every minute. It could go into a different measurement than a minute, but it's typically seen as a minute. And so cardiac output, or Q, you'll see it as just the capital Q sometimes for cardiac output. There's a formula to figure out, well, what that is. And so you can look at each of these pieces. And so there's two things that will determine how much blood your body moves every minute, and that is your heart rate, so the number of beats you have every minute, and the stroke volume, which is simply how much blood is ejected every time your heart beats. And so this is very dependent on training status and even gender and how big your heart is. And so every time your heart beats, you deliver a certain amount of blood, and you have a heart rate, which is how many times it beats in a minute. You multiply those together, you get cardiac output. And we can change stroke volume, how much blood is ejected with each beat, and heart rate through exercise or non-activity, and we can change this very quickly and over time. So here's kind of an example that just kind of lets you see the differences on what can happen. And so you have rest and you have maximal exercise, so working out as hard as they can. You have both males and females, so you can see those differences, and then you have untrained and trained. So generally what you see at rest is that trained individuals have a lower heart rate at rest than your untrained, and your stroke volume tends to be higher in trained athletes over untrained. But if you notice that the cardiac output is about the same for females and males. So males tend to be slightly higher, have a slightly higher cardiac output. It's needed, typically body mass is a little bit bigger, needs more blood to just keep living. Females tend to be a little bit lower, but at rest, the cardiac output's the same, but we get there different ways. So in trained people, they have a lower heart rate with higher stroke volumes, and the untrained, higher heart rates with a lower stroke volume. Now, in maximal exercise, these same people, their heart rates increase, and their heart rates, they get pretty close to the same, very high. But if you'll notice, the stroke volume the stroke volume stays higher in the trained person, and not as high in the untrained person, and it gets much higher in the trained male in this particular chart. And then what you see at the end of the day is that this translates into much higher cardiac outputs, which means you're delivering more blood, more oxygen, allowing you to run faster or run for a longer period of time. And this is why it makes such a difference over time, the changes we see immediately and long term when it comes to heart rate and stroke volume. And so we'll break this down a little bit, talk about each. So the heart rate, we've talked a little bit about, but your heart wants to beat naturally at 100 beats per minute, but there are things that can increase this and decrease this. And so decreasing heart rate is all through the parasympathetic nervous system, through the vagus nerve. And basically what it does is it slows the heart rate down by inhibiting that SA and AV node, and basically lowers that heart rate to where it needs to and thinks is appropriate. Your sympathetic nervous system, to increase heart rate, actually increases through, there are some nerves, so there are some excitatory nerves that increase it, but we also can increase it through things like epinephrine or adrenaline that we've talked about before. This can increase heart rate as well and work in combination. And so with that, again, the lower heart rate at rest is due to that parasympathetic. And then as you start exercising, the initial increase in heart rate is just a withdrawal from that parasympathetic nerve until you get up to about 100 beats per minute. And then we continue to increase our heart rate above 100 by giving it more of our sympathetic nervous system outflow from nerves and through some of the catecholamines that are released, like adrenaline and noradrenaline. This shows that connection to how that kind of nervous system is wired and where those are going. You can see there are direct connections into those SA and AV nodes. And this is just a cool chart showing you maximal percentage of exercise versus the heart rate, where those kind of stand, and that parasympathetic withdrawal up to about 100, and then the sympathetic outflow to keep increasing heart rate. This is something kind of interesting. Kind of read this on your own, talking about beta blockers and how that controls heart rate and how that can be useful in treatment, but also in different ways for exercise as well, and considerations. There's a new thing that, I say new, it's been around a little while, but it's becoming more accepted on something to look at when it comes to health and exercise, and it's called heart rate variability. And this is simply how much time is between your heartbeats. How much time is there between your heartbeats? We want to think it's very set. So if my heart beats now, and then a second later it beats again, then 1 second later it'll beat again. But if we actually time that out, it can vary greatly. I can have 2 heartbeats very close together, and then a longer break where I don't get a heartbeat, and then 2 quick heartbeats. And so what scientists have seen is that someone who has a healthy heart, the heart rate variability, so the time between their heart rates, the time between all of their heartbeats individually varies greatly. So some are really close together, some are far apart, and it's bouncing around all over the place. Someone who has not a healthy heart, their heart rate variability tends to be lower, meaning that there's this constant pace of their heart, and it hitting, every single time frame is about the same between beats. And so this is something you can kind of investigate. And so it's just another way for us to look at the healthiness of the heart as it comes to that. So then we move into stroke volume, and so we can also regulate stroke volume. We can change this to increase the amount of blood for every pump of the heart or decrease it. And so there's a measurement for this as well. And so there's end diastolic volume, which is simply an EDV, or the volume, how much blood is in the heart before it contracts. So literally, how much blood did we start with in order to know how much blood was in there when we started, so we can then figure out how much blood left if we know how much is afterwards. So that was kind of a weird way to say, but basically, if we know how much blood was contained in the heart before it started sending blood into the body, if we know that number and then we look and we can see how much blood is left in the heart after we send blood out, we can figure out how much blood moved into the body that the heart contracted. And so this is kind of used for that. And so the strength of our ventricular contraction, how much energy, how much strength it's using, is going to help determine how much blood leaves. And so we can actually make the heart contract stronger through things like adrenaline and noradrenaline to release during exercise, but also stress. But also there are nerves going to your heart besides the AV and the SA nodes that can tell your heart to contract stronger, such as like when you exercise, so that every beat you deliver more of that blood. You get more of that blood out that was delivered during diastolic volume. We also, within diastolic volume, have this really cool thing called Frank-Starling's law of the heart. So your heart will actually, as it fills full of blood, stretch out. And during exercise, you have more blood returning to the heart. And so your heart stretches out more. And that actually causes a more forceful contraction. So the more blood that is in the heart before it contracts, the stronger the contraction will be, and the more blood that will be delivered, a higher percentage of it will be delivered. And this is called Frank-Starling's mechanism, or Frank-Starling's law of the heart. And so this is really dependent on how much blood's coming back into the heart. And so this is something else that will increase with exercise. We want to get more blood back to the heart so we can take advantage of that. And so increasing that in diastolic volume actually helps us to move more blood to the heart and have a more efficient heart. And so this venous returning blood to the heart, is affected in several ways. So we have what's called venoconstriction, which is where we make our vessels smaller via the sympathetic nervous system. So nerves tell our vessels to go smaller. And so this is going to force the blood to move quicker through those and return to the heart sooner. Another way that this happens is through what's called a skeletal muscle pump. So when you use your skeletal muscles, the rhythmic motion of muscle contractions actually forces blood to move more quickly back to the heart. So when you exercise, when you move, you're actually forcing blood back to your heart quicker than if you're just sitting there, which is beneficial during exercise. So that means our blood's moving quicker and we can get more oxygen in it and get it back into the system quicker, so we can get more nutrients and waste products out. But it also helps that blood flow going back quicker to the heart for that heart to stretch out, and us use Frank-Starling's to even deliver more blood every single heartbeat as well. So it's not like we're just delivering more and can't utilize it. These two things in conjunction actually help. And then your respiratory, as you breathe, you're actually pushing blood back to the heart as well. And so if you're breathing more, which again happens during exercise, you're forcing more blood back into the heart. And so you can see how all of these things are needed for exercise individually, and then they combine to cause a greater effect so that these things can keep going. And so this is kind of that relationship to end diastolic volume, so how much blood is in the heart before it contracts. And then stroke volume, you see this kind of curve where it's going up, and those changes that occur. This is kind of just demonstrating a graph where you can see that skeletal muscle pump. There are one-way valves, so as your muscles squeeze your veins, it forces blood in one direction towards the heart, which is helping to increase that speed and increase the demand. If we didn't have these one-way valves, then what would happen when the muscles squeeze the veins? It would go in both directions, and we wouldn't get that increased return. So again, showing that stroke volume, this increase when you put the sympathetic nervous system into play, when those nerves innervate the heart, how the contractility increases, and how the fact we're delivering more blood with every single beat of the heart with that sympathetic nervous system, and how it relates to increasing amounts of blood into the heart as well. And so really what you're seeing is this cardiac output. You should be able to kind of walk yourself through this equation and how different parts of this are affected. So cardiac output is a very simple equation of stroke volume times heart rate, but what are the things that control the heart rate, and what are the things that control stroke volume? And so you should be able to kind of look at this as a good summary and explain what's happening here. And so This kind of changes. We start talking a little bit more about the blood. The blood is part of the circulatory system, and so we definitely want to talk about its characteristics as well. Um, and so there's really two parts of blood. We've got plasma, and plasma is the liquid portion of the blood. It's the watery portion. It's going to contain your ions like sodium, potassium, things like that. It's your proteins, your hormones that are being carried in the blood, nutrients. To some extent, the plasma is even containing some of the CO2 as well. But we also then have cells. So it's really made of plasma and cells. And your cells, we're talking about red blood cells. So these contain hemoglobin, which we all know carry oxygen. But when we talk about that, that's a lot of our blood, and that's very helpful. But it also is talking about our white blood cells, which are used in our immune system with helping to prevent infections and diseases. But we also have platelets, which are considered cells, and platelets help with blood clotting. So if you get injured, they go there, these platelets will form and help your blood to clot appropriately. And so all of these are important and make up our two components, our cell and our kind of liquid fluid portion. And so when we combine these, we get all of our blood, but sometimes it is good for us to kind of look at how much of our blood is cells and how much of our blood is liquid, and this is called a hematocrit. And so it's simply the percentage of the blood that is composed of cells. And it's pretty easy to figure out to figure this number out. You simply take some blood from somebody and you put it in a tube, and you spin that tube around in a centrifuge really, really fast, and it separates. The plasma goes on top. The cells go on the bottom. The red blood cells are heaviest, so they come there, and then there's a small layer of white blood cells and platelets, and you simply look at if this is 100 centimeters tall and 42 centimeters is where the cells are, then you would have a hematocrit of 42%, because that's 42% of the entire length. And so this is important. We kind of want it to be in this 50-50, maybe even like 45 area range where of your hematocrit, because we want this even distribution. If you have too much liquid, this could make for high blood pressure. This could make it where you can't carry as much oxygen as you need to per ounce of blood going somewhere. So that's important. But if we get it too high the other way, we have less liquid, and too many cells, our blood becomes very thick, affects hypertension, and may make us more likely to have a heart attack or stroke, because there are lots of other things in there, and clotting may occur. And so that's something for us to kind of note, is that the blood's important because the blood flow is proportional to a lot of things in the system. And so blood flow is how our blood is flowing is dependent on how much pressure there is, how much pressure is trying to force the blood to go through the system, divided by the amount of resistance that's there. And that hematocrit would change that resistance if it was one way. That's what we were talking about with increase in blood pressure. It makes our blood too thick, or there's too much of it. And so the resistance equation, that there are definitely some different parts of it, but it's just kind of good to know this. And again, just showing you this pressure kind of as we go through the heart and through our arteries and veins in the systemic circuit, is we start off with a very high pressure near the heart, and then as it moves through the system, that drops over time until it's basically at zero pressure coming back into the heart. So you're kind of slowing down because there's more and more of it. And so these all play a role in these hemodynamics of what's going to cause this resistance, okay? And that's why that's important, because resistance, there's a lot of things that can change this. So the length of the vessel can change resistance. The viscosity of the blood, how thick the blood is, can change the resistance, but also the radius of the vessel. And this probably has the greatest influence. So how big are arteries at? The bigger arteries are, the easier it is for liquid to move through them. The smaller they are, the harder it is to move through them. And so this plays a big role, but we can't forget about the fact the longer it is will play a role, and so will the viscosity. And so you have to take all of these into account when it comes to this resistance portion. And so this just shows you kind of, it's a good kind of pressure change that shows you how much the fact that arteries are going to play a bigger role in this pressure system than veins, and how that changes throughout time. What's happening here in this chart is it's showing you the resistance and the different areas of the vessels. And so arteries play a big role in this resistance. They can change size very easily. Veins don't change size as much so. And you see that you can actually see this pressure go up and down in our arteries because the heart's literally beating, right? The heart is beating high pressure and then low pressure when it's at rest. And you see this in your arteries, your left ventricle for sure, but in your arteries as well. And that kind of decreases to more of a stable and just continues to fall. And you don't see these spikes and lowering as you go through. And that's because these vessels are changing size. The length of them is going to be different, and how far away you are from that pressure source. And so that's really kind of putting that into perspective. So where that moves us to is starting to talk a little bit more about that exercise and what's happening. And so typically when we think about this blood and the cardiac cycle, the biggest thing we think about first is oxygen delivery during exercise and what's going on. And so realize that when you start exercising, there's more oxygen demand from the body. Your body needs more oxygen in order to produce energy. And this can actually go up to 25 times greater than at rest. So you need 25 times more oxygen during exercise than you may at rest. And so this O2 delivery is done by increasing that cardiac output, which we talked a lot about over the last few slides. And there's also this redistribution of blood flow to make sure that the oxygen gets to where it needs to be. If this didn't happen, we'd be delivering a lot of blood and a lot of oxygen to organs that may not need it or may not even be very active at the moment, and we want to get them to our working muscles during exercise. But in other times, this will shift. Our muscles may get less oxygen when they're not needing it, and other organs will get more. So during digestion, your oxygen demand goes up a little bit in digestion, and will take blood away from areas, maybe the skeletal muscle, maybe you're sitting, and send it to your digestive system to increase that. And so, again, in order to facilitate this, we've already kind of been mentioning it throughout. This cardiac output is going to make a difference. So we increase heart rate during exercise. Heart rate increases linearly with how hard you're exercising. So if you're on a treadmill and you increase the speed by 1 mile an hour, it's going to increase your heart rate by a certain number. And if you increase another mile an hour, it'll increase it by that same number again. And so there are your estimations for age predicted max. It's a little bit different in kids, and these are just estimates. They're actually not the greatest estimates in the world, but they give you a ballpark of how high your heart can get, and it is tied to age. We know that as you age, your heart rate tends to decrease over time. The other thing is that stroke volume. The stroke volume we talked about changing. That increases during exercise through all those components. But stroke volume actually stops increasing at around 40 to 60% of your VO2 max. So it does plateau. It plateaus there in most individuals. Highly trained subjects, they might see no plateau. It may slowly increase still because of that venous return throughout all of exercise, but it's not at 40 to 60%. It definitely doesn't increase at the same rate. It may increase all the way through, but when they hit 60% of their VO2 max, it slows down. It's not increasing as much. So a lot of our higher intensity exercises, our oxygen delivery is driven by heart rate alone and not with stroke volume. And so this goes on to talk about that stroke volume plateau in trained subjects not happening and why that may occur. Kind of tells you in your book where you can kind of focus on that. But other ways we work on delivering that oxygen is not just through, again, increasing cardiac output, but we're also going to change how much oxygen we can take out of the blood. So what happens is it's all diffusion. It's all a pressure gradient. And so during exercise, you're utilizing more oxygen at the muscle level. And so there becomes this higher differential. So there's less oxygen in the muscle and there's a really high level of oxygen in the blood. And so we have more oxygen literally moving into the tissue to be utilized than you did at rest. And so this is just simply a concentration. If you have a lot of water in a room it's completely sealed and there's none in another room and you open a door between the two, you're going to have a large influx of water into the second room. However, if there's not a big differential, maybe there's only a little bit more water in one room than the other, and you open the door between them, maybe only a little water goes through, and that's the same kind of thing going on here. And so what all this does is this starts to sum up and tell us that not only do we have the cardiac output equation, which is simple and can explain things, we also have a VO2 equation called the Fick equation. And the Fick equation basically is telling us how we calculate VO2, that volume of oxygen consumed. And the equation is cardiac output, which remember cardiac output is defined as heart rate times stroke volume, times our AVO2 difference. The more oxygen our tissues can uptake and utilize, the more we're going to be able to utilize, the more oxygen we're going to take in, the more we're going to utilize. And so we're going to see that full equation there. And again, all the different pieces that fall into that. And so this is a cool little graph just showing how things are changing with exercise, from heart rate to stroke volume to blood pressure and diastolic and mean. Realize diastolic blood pressure doesn't change during exercise because when the heart's at rest, and so that shouldn't change. It's actually bad if diastolic changes during exercise because when the heart rests, there's the same pressure on those arteries as there was during exercise. But you see this change in cardiac output, how it's steep until you kind of hit that plateau in stroke volume, and then it continues on being driven by heart rate and that AVO2 difference as well. And so this brings us back to that redistribution of blood flow. So we know that your skeletal muscles need more oxygen when you're exercising, and so that means they need more blood. So at rest, you're getting about 15 to 20% of the cardiac output. So we're not saying a particular amount of blood. The amount of blood goes up greatly when you start exercising, but so does the percentage of blood being that your body's actually moving. So 15 to 20% of the blood you're moving right now through your body is going to your skeletal muscles. During maximal exercise, about 80 to 85% of the blood, your heart is moving. So it's moving a lot more blood, and you're getting about 80 to 85% of that going to your muscles, showing you how much of a demand it has. And so at the same point, if we're delivering more blood to some places, we need to decrease blood flow to other places because we only have a finite amount of blood. And so we decrease blood to your liver, your kidneys, your GI tract, because you're not digesting during exercise, which is why some people get upset stomachs if they eat real close to exercise. Also realize if you've been exercising, typically if you use the bathroom before you go exercise, you're not going to need to during it because we're reducing kidney level because we're not worried about cleaning the blood. We just need to get oxygen there. But it's a lot of things. Realize your brain is always going to maintain the same blood flow regardless. The percentage might change, but it's always going to maintain the exact same amount of blood flow during exercise and rest to keep you functioning properly. It doesn't need too much, that's bad for it, and too little, we pass out. And so that's just something to kind of note. Let's see. And so this graph kind of shows you some of those changes that you see occur. This chart's great. It shows you what stays the same, what is kind of increasing percentage-wise and decreasing during exercise, and showing you kind of what's going on there. And so those are some really good charts, as you can see. So the regulation of local blood flow during exercise for skeletal muscle, it's through vasodilation. This is auto-regulated. There are sensors that open up sphincters that allow more blood flow to come in. They vasodilate them, and it senses this change in O2 and CO2 demands. The vasoconstriction and things like your digestive tract, this is controlled by your brain, so the sympathetic nervous system, and it literally has sphincters in those blood areas and cause your smooth muscle to contract and reduce that blood flow from resting values. So we do have this thing called nitric oxide that your body produces, and it produces them. Your body produces them when it needs them, and this causes vasodilation to occur. It's kind of that auto-regulation area. And so when it realizes it needs more blood flow to an area, your body will produce this nitric oxide in that particular area, cause the vessels to vasodilate to improve blood flow. And so that's kind of what's going on with that autoregulation at the muscle level. There are other things that go into it as well, but this is one of the factors that we know about. And so we've talked a lot about general changes to heart rate and blood pressure as we exercise, and typically we're thinking of whole body exercise, something like running. But our exercise actually does kind of control this heart rate and blood pressure response. So we're very used to leg exercises, and we know what's going on there. But if we do arm exercises only, so you're doing something just with your arm, maybe you're cycling with your arm, or you're just going with your arms only. You're sitting in a chair and you're doing something with your arms. Look up arm ergometry. This is kind of what I'm thinking about in my head. This is actually going to cause heart rate to increase quicker, and it's actually going to increase your blood pressure more, because what's happening is you have a lot less muscle mass in your upper body than you do your lower body. And so if you're just using your arms, you see this really quick increase in heart rate. You're delivering a lot of blood, but there's not as many muscles vasodilating to take that blood. And so you see this big increase in blood pressure as well when it comes to that. And you're actually not going to hit as high VO2 because you don't have the muscle mass to consume as much oxygen. We also know that over time, if you exercise for a really long time, heart rate can continue to creep up over time, just to kind of keep cardiac output up as it becomes harder to maintain. And then of course intensity, we all kind of get the intensity thing, and hot versus humid and cool environments. So if it's hot and humid, tends to be your heart rate and blood pressure will be higher because you're trying to cool yourself off, and you're also losing blood volume due to sweating. You're losing water volume, which changes blood volume, versus a cool environment. Emotional factors, so stress can play a role in this, and what's been going on in the body can change these during exercise, but also just sitting here. And so we also talk about how things change between initial spots and then steady state. And so at the onset of exercise, at the very beginning, a very rapid increase in all of these to try to get up to steady state. And then after you get to steady state, if you increase intensity, it usually goes a little bit slower because your body's kind of caught up. But if you go above lactate threshold, you'll see all of these continue to slowly climb as it tries to deal with the byproducts and the energy constraints that your body has changed. During recovery, you see all of these things decrease, trying to get back to homeostasis, but they will stay elevated for some time after exercise, depending on how hard it was and how long you went, because you're trying to recover as well, right? You're keeping elevated heart rate and stroke volume to clean out waste products to help the muscle recover and rebuild and all of those. And so that is part of it as well. And so you can kind of see this recovery of these different things from rest to exercise and back, and what's staying kind of elevated. Remember that epoch we talked about. Let's see. We talked about these linear increases with heart rate and blood pressure as well. Let's see. So one thing that is a good kind of another way to measure, because sometimes people have blood pressure issues or have heart rate issues, or maybe they're not at a steady state completely, is we have this thing called double product, or rate pressure product, or double pressure product is sometimes the way it's referred to. And this is a way to see kind of how much load is being put on the heart by basically there's no unit to it really. I mean, there is a unit you can define to it, but there's no like set value that it's at, but it's basically taking heart rate and multiplying by systolic blood pressure. And this helps to indicate how hard the heart is having to work, especially if someone's on a medication or had some kind of issue that's occurred with their heart where things don't function quite as we would always expect, and heart rate maybe has changed due to a medication or something, or stroke volumes affect because of a heart attack. We can still use double pressure product or rate pressure product to help know how hard the heart is working, from heart rate times systolic blood pressure. And it's another way to measure that. It's another way to look and kind of gets rid of some of the variables of inconsistencies that may happen person to person due to having different physiology or other things affecting their heart rate and systolic blood pressure. And so this gives you you can see how that may look with double pressure product. This would be in a healthy individual, but maybe someone is not as trained, and we're trying to see how hard their heart's having to work, and maybe they're at a heart rate of 100, but their blood pressure is 200, and so we might have a much higher number, and we can still kind of track those kind of changes going on. We talked about arm versus leg already. These are some graphs that kind of show you those blood pressure and heart rate changes related to that. Let's see. I think we've covered all of this as well. Heart rate recovery response following heavy resistance training. So you can see how after multiple bouts of heavy training, it takes longer. The heart rate doesn't recover as much. So if you're doing this intermittent exercise or HIIT style training, you're going to watch the heart rate continue to go up even at the same workload, because it never truly hits steady state. It's working towards that steady state. Prolonged exercise, you will see a gradual decrease in stroke volume. Again, you're losing blood volume from the sweat typically because of dehydration. And you'll see heart rate kind of drift up. It's called cardiovascular drift, and that's so you can maintain the same cardiac output. If stroke volume goes down, the only way to keep a cardiac output the same is to increase heart rate. And again, you'll see that kind of here. So one thing to note with the cardiovascular system is exercise is very, very safe, but there are chances that things do occur. And so exercise can cause what's called sudden cardiac death during exercise. It's very uncommon, especially in youth. It does go up as you get a little bit older. Typically, there's an underlying condition, some kind of heart defect that was not detected that caused this. It's very unlikely to happen, but it does, and this is why you see some people pushing very hard for echocardiograms for athletes, even at the youth level, that they have to get them to participate to kind of help catch these problems before they unexpectedly end a child's life. But with adults, this number goes down a little bit. They become a little bit more common, especially as they get older. But again, exercise is relatively safe, even in those who've maybe just had a heart attack or had a major medical condition. They just need to be monitored a little bit more and not pushed quite as hard. But a medical exam from a doctor is always a good idea for anyone who's going into exercise, but especially those who may already have heart conditions, just to double check. But exercise is actually recommended for almost anyone, regardless of what kind of disease they may have. And so at the end, really it's a summary of our cardiovascular response to exercise from cardiac output and blood flow. And you should be able to kind of start connecting all of these pieces and how they would fit into kind of that FIC equation, cardiac output equation, and what these look like. I think this is getting close to the last thing, is there's this central command theory that basically initial signals for the cardiovascular system are driven by our brain. They're kind of driving these initial big changes we see, and then all the fine tuning to get things into steady state and get them at the appropriate levels once we get kind of close to where we need to be are done kind of through feedback mechanisms through the heart and muscles that detect different chemicals and different ratios. And so it's a pretty cool idea to think the fact that if you jumped up out of your chair and started exercising, you're going to see these big changes due to the brain just getting everything running, and then all these other receptors and sensors are going to help fine-tune that to be exactly where you need to be, so you're not wasting energy or not having enough and leading to some of these issues that would occur, so you can exercise at your best. And again, this is just kind of looping that back in to the whole system. So that covers this lecture. If you guys have any questions, please shoot me an email, and have fun as you continue to cover the material for this course.